Good morning, everyone. So, we'll be seeing the topic of convolution today in your module 2 of signals and systems. So, convolution is one of the ways of representation of an LTI system. The other two methods are the differential and difference equation representation and the block diagram representation. The convolution is called as the impulse response representation of a system because for an LTI system, here we can write the output as the convolution of the impulse response and the input of a system. So given any input to the system and you know the impulse response of the system, you can find the output of an LTI system. Convolution when applied to discrete time systems is called as convolution sum, and when applied to continuous time systems it's called as convolution integral. So let's derive the equation for convolution sum. So what do we do in convolution sum is, first of all, we try to represent the input as a weighted superposition of shifted impulses. So what does this mean? So let's consider an example for this. So here we have a signal x of n, right? And we want to write this as a weighted sum of impulses. So if you look at the signal x of n, it is nothing but a set of impulses which are also shifted, right? So at n is equal to 0, we have an impulse with a weight of x of 0 or the amplitude. Then at n is equal to 1, we have another impulse which is shifted to the right and having an amplitude x of 1. And then towards the left, you have impulses which are shifted to n is equal to minus 1, n is equal to minus 2 and multiplied with its corresponding amplitudes, right? So we can write this signal as a sum of these shifted impulses. So why it's called as the weighted sum? Because every impulse is multiplied with the weight or the amplitude of that particular impulse, right? So this in the form of an equation can be written like this. So x of n is a sum of impulses written in this fashion. In the compact form, we can write this as a summation of x of k into delta of n minus k. Let's give this input to the LTI system, and therefore the relationship between x of n and y of n can be written in this form, right? So y of n is the output of the system H where the input x of n is applied. Now, x of n is written as in the compact form as a summation of x of k into delta of n minus k. So, h on this. Now, the system is a LTI system, so therefore it has to satisfy the linearity property, right? So, if we apply the linearity property to this equation, then the operator and the summation can be interchanged by applying the linearity property. So, that's what I have done here. The operator on x of k into delta of n minus k is what we have. X of k are the constants because they correspond to the amplitudes of the discrete time signal. So x of k are constants and therefore x of k can be written outside the operator h, right? Then you know that the response of a system to an impulse input is called as the impulse response and is represented as h of n. So now, since the system is time invariant, we can apply the time invariant property. So if you shift the input, that is delta of n as delta of n minus k, and apply it to the system, the output also gets shifted by the same amount. So that's h of n minus k. Therefore, h of delta of n minus k can be written as h of n minus k, right? So this equation what we have obtained here is the equation for convolution. It's the equation for convolution. That is summation x of k into h of n minus k. This in a compact notation is written as x of n star h of n. So the star symbol indicates the convolution operation. Okay. So as you can see, initially we started off with writing the input as a weighted sum of shifted impulses. So now the output will also be a weighted sum of shifted impulse responses. Okay, so that's how we obtain the output y of n of the system. So you can understand this concept better by looking at an example, right? So let's take an example. Yeah, so before that, what is convolution integral? So like we derived the equation for convolution sum, the convolution integral is also based on the same lines. So where your input is a continuous time signal x of t and the output y of t, and this will be the equation for convolution integral. What's the difference? We had a summation symbol there and you have an integral here because these are continuous time signals. Okay. So let's solve a problem in continuous time integral, and that will make you understand the concept better. So how do we perform this process of convolution, right? So before that, just observe the signal, the equation. Two signals will be given to you, x of t and h of t, and you will be asked to find the output y of t. Okay. So when x of t and h of t is given to you, we have to first obtain x of tau and h of t minus tau, right? Then multiply the two and then integrate. So how do we do that? Let's take an example like this. So here a continuous time LTI system is given, which has an impulse response h of t equals u of t, and the input is a decaying exponential signal multiplied with the unit step. So let's plot x of tau first. So x of tau is, x of t is given to you. Just change the variable to tau and plot x of tau. So a decaying exponential signal starting at the origin and tending to plus infinity on this side. So simple, x of tau is plotted. Then you have to plot h of t minus tau. In order to plot h of t minus tau, the procedure is first plot h of tau. So here h of tau is a unit step signal which is given, and that's what we have plotted here. Then fold the signal. Okay, fold h of tau to get h of minus tau. So h of tau is folded and you get h of minus tau where the signal looks like this. The next important thing is to get h of t minus tau. Okay, so to get h of t minus tau, what you have to do is just call the origin point in your h of minus tau as t. So this signal now becomes h of t minus tau. Very simple, right? Now you need to shift this h of t minus tau for different values of t and obtain y of t and obtain the output y of t. So how do we do that? Now look at this, x of tau you have, h of t minus tau you have, right? So for this particular case, that is when your t is less than 0, here the reference axis is tau for us. So for t less than 0, what is your output, or what is rather the product x of tau into h of t minus tau? It's definitely 0, right? Therefore your output y of t is also 0. Then let's move the signal further. So if you bring this t more than 0 or t greater than 0, then this could be one possibility. The signal, this is how it looks like. Now if you look at the product x of tau and h of t minus tau, it is not equal to 0, right? So we can write an equation for y of t. So for t greater than 0. So what is that equation now? So integral x of tau, the equation of x of tau is e power minus a tau. H of t minus tau, the amplitude is 1, so I have written 1, and d tau. The limits, so from where to where are you multiplying x of tau and h of t minus tau? From 0 to t. Therefore, the limits are from 0 to t, right? Simplify this, integrate this, substitute the limits, then you get an equation for y of t. You get an equation for y of t, and this is for the condition t greater than 0. So you move this t anywhere up to plus infinity, the overlap will not change, nor the interval 0 to t is going to change. Therefore, this will be the output equation y of t for t greater than 0. Yeah. So what is your output y of t? It is 0 for t less than 0, and the value 1 minus e power minus at by a for t greater than or equal to 0. Right? So this in a compact form can also be written as 1 minus e power minus at by a into u of t. Yeah. So that's the concept of convolution. And in the next class, we'll take more problems and try to solve these problems on convolution. Okay. That's it for today. Thank you.